in the second half of Chapter 9, we're going to continue to discuss rotational motion. The first half's really pretty simple. Once you understand that the equations of motion look the same, whether it's rotational or linear motion, it's just a matter, do you mean a linear velocity v or an angular velocity omega? They're pretty easy. There continues to be a corollary, but it does get a little more difficult once we start introducing concepts like energy, momentum, something called torque. So today we're going to really look at using energy and the idea of conservation of energy to solve problems. But in order to do that, we have to introduce something brand new, and it's called the moment of inertia. Now this is a quantity that describes how the mass is distributed around the center of rotation. Often it's very symmetrical. If you have something like a rotating disc, usually it rotates about an axis through the center of the disc. Same for a sphere, but not always. You could have it rotating again through some other axis. The quantity, the moment of inertia, is given by this I equals mass A times RA squared plus mass B times RB squared plus mass C RC squared. And each one of these masses is a point mass that makes up this solid. So you could have hundreds, if not thousands, of point masses that make up this solid object, okay? Notice as mass gets farther away from the center of rotation, because this is the distance r is to the center of rotation, the moment of inertia for that particular particle of the mass increases. Obviously, we get an SI unit. That looks like kilograms, that's for the mass, times meters squared. Now, let's just look at a simple example. Let's suppose that we have 4 point masses. And I'm making this problem up even as I work it. We're going to let them be point masses, and they're attached to by a thin rod. And the reason this is a thin light rod is we don't really want to worry about the moment of inertia for this rod. And they are going to rotate about an axis right there that points out of the board. So I'm going to let this be 2 kilograms, 2 kilograms, 2 kilograms, 2 kilograms. I'll make it nice and easy. And each one of these is 3 meters. So if we're rotating about an axis right here, rotating about point A, as long as the rods or whatever that is attaching all these points for this solid are really, really light, and all of the mass is concentrated at these little spheres I put on the end, I can calculate a moment of inertia that looks like this. The moment of inertia for that particle is 2 kilograms times 3 meters squared. Well, in fact, that is the moment of inertia for all 4 of those particles. So that would be 2 times 9, that's 18. 18 times 4, that's 72 kilogram meters squared. That's if they're all rotating about that point in the middle. There's other points we can rotate about. What if we decide instead we're going to have everything rotate about point B right here? That's point B. And what if I say that this mass, there's a point right here where they're connected, is 5 kilograms, just to be different. This will be a slightly different problem. So if we rotate about point B, I'm not sure I even really want to do this problem, but we could, because I don't know these angles. I'll tell you what, let's change this up just a little bit. I just want to do something that's not perfectly symmetric. Let's put 3-point masses connected. Again, let's let them be really light rods. 2 kilograms, 4 kilograms. One kilogram, 3 meters, 4 meters, 5 meters. That means that's a right triangle. If we want to, that looks very different. But suppose that I have a rod, I consider my axis to be right here along this line. Well, if I'm rotating about this line, what you'll notice, when I do the moment of inertia, if I start with the 2 kilogram mass, it has a distance of 0 from the axis of rotation because it's actually on the axis of rotation. The point that is on the axis of rotation actually has a moment of inertia of 0. The same for this point down here. It's on the axis of rotation. And then finally, this point is 4 meters from the axis of rotation. That's going to end up being 64 kilogram meter squared. So really, if we're just talking about a few point masses and we can see for sure how far they are from the center of rotation, you can calculate a moment of inertia. Okay, but most of the time when we calculate a moment of inertia, we're doing it for something like a sphere or a disc, and these things take calculus, and it makes a difference. Is that a hollow sphere or a solid sphere? If you have a, let's look at that. To really and truly calculate a moment of inertia, we need calculus skills, and we don't have them. So we're going to use basically moments of inertia that have already been figured out for us. One is for a solid sphere. If you have a solid sphere, and it is revolving around an axis through the center, so we're talking about put an axis right through its center that it's going to spin around, its moment of inertia is 2 PHYS mr squared. R is obviously the radius of the sphere. That's a solid sphere. If you have what we call a hollow sphere or a very thin shell, again, it's the same look, it's a sphere. It's got a radius of r. But if all of the mass is on the outer surface, that it's empty inside, we find that the moment of inertia is 2/3 mr squared. So that's a hollow sphere. What that means is if you have two spheres and they have the same mass, and they have the same radius, they will have a different moment of inertia. Here, the moment of inertia is actually larger because all of the mass is on the outer side of the sphere. It's farther away. In the solid sphere, we have that same quantity of mass evenly distributed throughout, so many of the mass points are closer to the radius. So you see they're not the same. We use these two a lot, and we'll use disk a lot. A solid disk looks like a wheel, so think of something that looks something like this. Again, this has already been calculated, so this is a solid cylinder. I is 1/2 mr squared. And finally, we have what we call a cylindrical shell. This is where you have what essentially looks like a disc, but it's just a ring. So if this looks more like a dinner plate, this looks more like an embroidery hoop. It's just a ring around the edge. And its moment of inertia for this cylindrical shell is I equal mr squared. Again, you'll notice it's got twice the moment of inertia if they have the exact same mass. Again, that's because all of this mass is at this distance r, and we'll just draw r kind of to the middle because we're assuming this is a very, very thin, just like here we're having a very thin shell. If you don't have a thin shell, it is possible to calculate a moment of inertia for something that is a thick shelled, where you have like more of a donut type shape, but we're not going to use that. So these are our basic formulas for moment of inertia. Now, okay, the moment of inertia tells you something about how the mass is distributed about the axis of rotation. So what? Why do we care? We care because it plays an important role in how the object will actually rotate. It takes more energy to rotate an object that has a higher moment of inertia than it does to rotate something with a lesser moment of inertia. In fact, rotational kinetic energy. We know if something's moving, it has to have kinetic energy. But at the beginning of the semester, everything was a point mass, so everything had translational kinetic energy. It either moved horizontally, it moved up and down. But in this chapter, things can actually stay in the same place and just spin. How much energy does it take to spin? Rotational kinetic energy. If I was going to abbreviate that, I would probably put it a capital K with the R. The R tells me that it's rotating. Get a little better pen here. And that equals 1/2 I omega squared. 1/2 the moment of inertia times the angular velocity squared. If we're talking about translational kinetic energy, that's 1/2 mv squared. So it's like if we were learning our secret code and A turns into alpha and V turns into omega, the mass turns into the moment of inertia in all of the formulas that we're used to. It is entirely possible to have an object that is both spinning and translating. Think about a car tire rolling down the road. The tire is spinning, it's also translating, okay? So we're going to look at some problems that deal with rotational kinetic energy. In this example, it says a cable is wrapped several times around a solid cylinder. In other words, you'll see a lot for a solid cylinder would be a solid disc that has a mass equal to 50 kilograms And it says a diameter of 0.12 meters, but I think I'll go ahead and say that its radius is 0.106 meters. Just saves a little space. So we know the mass, we know the radius. That means I can easily find the moment of inertia for a solid disk because we have the formula for that. A constant force of 9.0 newtons is applied and unwinds the cable. .0 meters. What is the final angular velocity which of course is omega, and final angular velocity of the disk and linear speed of the cable. Now, here's the picture. Here's the disk. There's the center of rotation. It's like those pull cords you have on a lawnmower, and it's got this cable that's wrapped around it. But it's got a little handle here or something. You're going to apply force, pull it. You're going to pull this for 2 meters with a constant force. So let's suppose that you're taking this point right here. There's the little handle on the pull. You pull it 2.0 meters. You didn't work on this cable disc system. Make sense? The work you did is 9 newtons times 2 meters, or 18 joules. All right. They didn't ask me how much work I did, but that to me is the key thing. If I know that I applied a certain force for a certain distance, I know how much work I did. That work went into changing the kinetic energy of the disk. That's the work energy theorem. In this case, if the initial kinetic energy is 0, then the work will simply equal the final kinetic energy, right? Because this is work equals K final minus K initial, but that was 0. So 18 joules equals 1/2 I omega squared. All that work went into rotating that disk. We are assuming that the rope, and I think it probably has this in the fine print, is of negligible mass. So it's going to have the rope itself will have almost none of this kinetic energy because it doesn't have any mass. It's like super fine. Okay. I need to get this, and I can solve for that. What's the moment of inertia? I have to look that up. It tells me in my previous page that for a disk, a solid cylinder, it's 1/2 mr squared. So I have 18 joules. 1/2, I is 1/2 times the mass, 50 kilograms, times the radius squared, 0.06 squared. So put that kind of in a bracket so you can see that. All of that that's just I. That's our formula, 1/2 mr squared. So we could have calculated this separately, but that's the moment of inertia for a solid disk times omega squared. This is just algebra. I can go through all that algebra. When I get done, I come up with 20 radians per second. So I know that the disk is spinning, this disk right here, spinning with omega, is 20 radians per second. I haven't answered the question about the linear speed of the rope, but the linear speed, if the rope is wrapped around the disk, the final linear speed of the rope is directly related to the final rotational speed. You're just saying, well, how fast is the point on this edge moving? We can use V equals R omega. So 0.06 times 20, and that is 1.2 meters per second. I'm 99% sure that this example comes straight from the textbook, so you can read through this problem in its entirety if you want to kind of brush back through it. But what were the key things? They told us the force and the distance. We could calculate how much work was done on the system. And we made the assumption that all of the work was going into the rotational kinetic energy of the disk. We can do that if the rope has no mass. I know that's a little bit of a stretch. Otherwise, we would have to actually include the rope also. We'll look at problems where we do kind of have to include a bit more, but for now, we'll just say the rope didn't use any of the energy. I can use work energy. I just have to remember that in this case, rotational kinetic energy is 1/2 I, moment of inertia, omega squared. You've got to calculate that I. They gave you the mass, they gave you the radius, 1/2 mass times radius squared. We can do that. No problem getting our answer. All right. Let's look at another problem. In one edition of the book, this was problem example 9.8. I can't guarantee if they've changed that number, but you'll recognize this problem. Deals with conservation of energy. In this problem, we have a well. Part of this well is underground, part of this well is above ground, but here's the water level. Up above this, we've got a rod, which is a cylindrical rod. That's a solid cylinder. It's a really small looking solid cylinder, but a rod is a solid cylinder. It has a little handle on it. So you can crank it up or crank it down. And it's got a bucket. Okay, there we go. There's our bucket. The question says, we'll call this H from here to where the water is. This is the water down here. Okay. So I've got a well, I have a bucket that's a distance H above the water. I've got a rod. They give me information about this rod. Has a mass That's M. It has a moment of inertia. That is 1/2 mr squared. Because, of course, it's a solid cylindrical rod, so that would be the formula for its moment of inertia. Its radius would be whatever the radius of this little cylindrical end is. I also have a bucket. It has a mass M. The entire system is at rest, and then the handle falls off. Let's see. The handle falls off, and when the handle falls off, the bucket starts falling. Now the bucket's not in free fall because it's got the tension in that cable pulling up, right? It's not in free fall. It's kind of complicated, but if we think about it in terms of conservation of energy, it's actually not that hard. The question wants to know, can we find the speed of the bucket I don't want to know the speed after it. I want to know when it strikes the water, how fast was it going? Because I know as soon as it hits the water, it's going to start to slow down because it's going to have interference. But when it falls, it's going to accelerate downward because there is gravity. How fast will it be going? All right. They don't give me any numbers. So I have to do all of this in terms of H and G and little m and b. I can do it though. And I do it with thinking of conservation of energy. Conservation of energy says my initial potential plus my initial kinetic equals my final potential plus my final kinetic. Now, remember, only changes in potential energy are really significant. I don't really have to know how high this rod is above the water because there's not going to be any change in gravitational potential energy of the rod. The only change in potential energy is going to be from the bucket. The bucket, which is little m, starts off with mgh. The whole system is at rest. So at the beginning of this problem, all of the energy is just the gravitational potential energy in the bucket. That makes sense. The bucket starts to fall. When it reaches the water, based on where we decided to call 0, all of the gravitational potential energy will be gone. Well, where did that energy go? It went 2 places. When that bucket falls, that gravitational potential energy went into the kinetic energy of the bucket, 1/2 mv squared, plus the rotational energy of the rod. It took energy as that bucket is pulling down. It takes energy to spin this rod. How much energy? 1/2 I omega squared. This gets to be fun. This is where we're going to do some thinking. All right. They just want me to solve for V. I have to get everything in terms of M or either M or G and H. So I'm allowed to have M's, R's, G's, and H's. I don't even know if I'm going to need all of those. So here's what we've got. MGH equals 1/2 mv squared plus 1/2 I. All right, for For a rod, I is 1/2 capital M R squared. There's one more substitution I want to make. I want to get rid of omega. If you remember, V equals R times omega. In this case, this would be capital R, because it would be the radius of this disk, whatever that little tiny radius is. So the rotational speed times the radius will tell us a linear speed for this. So I can rewrite omega as V over R. So instead of omega squared, I'm going to put V over R squared. Omega is equal to V over R. That's a really important idea in these problems. All right. Now what happens is these R's cancel out. That's an R squared. This is an R squared. I get MGH. I might as well, let's see, equals 1/2 MV squared plus 1/2 times 1/2 is 1/4. Capital M V squared. I'm going to have to go back up to the top, but I've gotten rid of everything except M, G, and H, and I need to solve for V. I'm going to factor the V squared out. If I divide, I get 1/2 M plus 1/4 capital M. I'm dividing by all of that. And I have to take the square root. If we knew some numbers, we'd really have our answer. I don't really like the complex fraction down on the bottom. Not too crazy about that at all. So I might want to go ahead and multiply the numerator and the denominator, if I wanted to, by 4. If I multiply, look at the bottom, if I multiply by 4, that's going to be 2 little m plus big M equals 4 mgh. All right, it's always good to stop and think about whether or not this makes any sense. If the rod had a mass of 0, this went away. This will turn into V equal to the square root of 2gh, because I could just, if this was 0, I could divide by 2. That's the velocity for free fall. So that makes sense. If this rod up here had no mass, well, then the bucket would be in free fall. It'd just be falling. That makes sense. On the other hand, we can also see if M gets really, really heavy, infinitely large, much, much bigger than M, the velocity would be virtually 0. That also makes sense. You think if the mass of the bucket was very, very light and the mass of the rod was extremely heavy, it would make sense that the acceleration downward would be infinitesimally small. In reality, it would probably be 0 because of friction. But you just want to kind of look and think about what happens? What happens if m is really, really big? Well, then the velocity is very small. What happens if m is 0? Well, that just reduces down to free fall. So our results kind of make sense. Not kind of, they do make sense. Okay, we have one more type of problem we want to look at. And that's a problem where we have to kind of consider both what happens when an object is rotating and translating at the same time. This is section 9.5 in your book. I have no idea what example this is, but it involves a yo-yo. Suppose we have a solid disc yo-yo. Well, a solid disc has a moment of inertia equal to 1/2 mr squared. We use that one a lot, so it's one I kind of have memorized. If we start with this disc up here, and it's got a string around it like all yo-yos do, so this is some height, and we let it fall, it unrolls till it's down here. The distance from here to here is h. So you ever played with the roller, so you just let the yo-yo drop down and fall some distance, okay? It says, find an expression for the velocity after it falls. So this is another conservation of energy problem. Initially, we're going to let it start from rest. Initially, it has only gravitational potential energy. That's mgh. It doesn't have any kinetic energy because before we let it go, it's neither rotating nor translating. When it reaches the end of its string and it has dropped this distance h, it has actually had both. It has no potential energy, but it has both kinetic and rotational. Again, this should be the capital N because that's the mass of our yo-yo. If we fill in, we can make a couple of really important things. One is this whole idea that relates when you have something rolling with a string or a tire rolling along a road, there's a definite relationship between how fast this is rotating and how fast it's moving horizontally or vertically. If it's a tire on a highway, it's going to be horizontal. If it is a yo-yo on a string, it's going to be vertical. But we know that the speed is r omega, which means that omega is v over r. That's a really important substitution that we use a lot on these problems. The angular velocity equals the linear velocity divided by a radius. That's a relationship for a point that's on the edge of the disc, or the edge of the tire on the road. All right, I have mgh. This was 0. 1/2 mv squared. 1/2 I. Well, I is 1/2 mr squared times omega squared. Omega is v over r squared. Here's my moment of inertia. Here's my angular velocity in terms of v, in terms of the linear velocity. Again, pretty miraculously, these R's cancel. These come out to look just alike. I get MGH. 1/2 plus 1/4 is 3/4 MV squared. Now, by now, hopefully you're all in your mind saying, Mrs. Hughes, why haven't you canceled out those capital M's yet? Obviously, the velocity is not going to depend on the mass of the yo-yo. Okay? All three of these forms of energy are related to this same mass with the yo-yo, so we don't need to keep, there's not two different masses in this problem. So we can cancel those out. Again, if we solve for V, we get V squared is multiplied by the reciprocal, 4/3 GH. So V is the square root of 4/3 GH. What was free fall? It's a good one to know. When something's in free fall, it's fine after it falls a distance h. Its velocity is the square root of 2GH. So 4/3, 1/1, it's less than 2. I would expect the velocity to be less than free fall. I expect it to be a number smaller than 2GH, but you can see it's going to have all the right units. It's going to be 4/3 GH. If we did this same identical problem, in fact, let's do the same identical problem, but instead we make the cylinder hollow. So now instead of having the solid disc, we have a hollow disc. I switched to the blue because the blue is a better marker. So if I have a hollow disc, my moment of inertia for a hollow disc is simply mr squared. The relationship here has not changed. V is equal to r omega. So let's just go ahead and write our previous. We know for the solid sphere, it was 4/3 GH. Now let's stop and think. Would we expect a hollow sphere that has a larger moment of inertia to be going faster or slower? All my instincts say that if the moment of inertia is larger, that means more kinetic energy has to go into rotating, which means less kinetic energy can go into translating. Right? We only have a certain amount of energy, mgh. The more energy that's required to rotate, the less energy that will be available to translate. So by the time it's fallen this distance, I think it should be moving slower. So let's look and see what happens. Let's go back to the beginning just for the practice. So here's my free fall is this. This is my solid cylinder. And I want to see what happens when I get to that hollow cylinder, or that thin-shelled. Okay. MGH, no potential energy at the bottom. Here's my kinetic, 1/2 mv squared, plus my kinetic energy, my rotational, 1/2 I omega squared. I is going to be mr squared, and omega is v over r squared. 1/2 I omega squared. The r's cancel, and this comes out to be mgh, sorry, that's a capital M, equals 1/2 mv squared. This also comes out to be 1/2 mv squared. I don't need the m's. 1/2 plus 1/2 is just 1. I get GH equals V squared. So yes, the hollow one is even slower than the solid one. As you increase an object's moment of inertia by redistributing the mass farther from the center, if you don't change the radius, you don't change the size, more of the energy will be required to rotate it and less energy will be available for translation. I'm going to work one more problem that's related to this idea. Okay, we have a solid sphere and for a solid sphere, I is equal to 2/5 mr squared, and we have a solid cylinder. That's I equal 1/2 mr squared. Notice 2/5 is only about 4/10. It's exactly 4/10. 1/2 is 5/10. So this has a slightly larger moment of inertia. This one's going to require a little more energy to rotate because it has a little higher moment of inertia. But they have the same mass. They have the same radius. So the radius of the sphere and the cylinder are the same. All right. Suppose there is a ramp. They are going, when they reach this ramp, and you can't see both of them at the same time, but they have a velocity of 6.50 meters per second. That's a linear velocity. And they are going to roll up the ramp without slipping. It's really important that they're not slipping, because if things start slipping, that changes our problem. So they're just going to roll right on up the ramp. And the question basically says, what's the maximum height of each one of them? How high will they go? That's really a question of when will all of its mechanical energy or kinetic, all of its kinetic energy be converted into gravitational potential energy. So we're going to start with just this whole idea. At the beginning, this object is spinning, it's rotating, and it's translating. It's really important to remember it's rotating because it's spinning, and it's translating because it's moving either horizontally or up and down or at some angle. So we have our initial, let's do the sphere first. We're going to look at the sphere. For the sphere, it starts on the ground. This is 0. It's kinetic energy. It has two types of kinetic energy because it is translating and rotating. It's 1/2 mv squared. I do know v. Well, I'll tell you what, let's just leave it 1/2 mv squared plus 1/2 I omega squared. And that has to equal mgh plus 0, because at its highest point, it has stopped. It will roll up, it will momentarily stop, and then it will roll back down. All of these are capital M's. All right, so we're doing the sphere. 0, we have 1/2 mv squared, 1/2 I is 2/5 mr squared. Omega, we still use that same relation. V is r omega. Omega is v over r. and it is squared. And of course, there's no, oh, do I have everything? Yes. And this equals mgh. So it will stop when all of this kinetic energy has turned into this potential energy. And I can actually get problems on this, numbers on this, because I know if I look at this, I'm trying to solve for H. I know V. The R's are going to cancel out. So let's just keep going. The M's cancel out. Let's go ahead and cancel all those M's. M, M, M. So 1/2 6.50 squared. 1/2 times 2/5 is 1/5. 1/5. The R's cancel. So this is 1/5 V squared. Equals GH. That's just put in the numbers. 1/2 times 1/2 V squared, 1/5 V squared. When I put in all of the numbers, I get that H is 3.02 meters. So if we're doing the sphere, we found that H will be 3.02 meters. Okay, let's go back and think. A cylinder takes more energy to rotate. It has a larger moment of inertia. That tells me it won't reach as high a height. It's not going to go as high as our sphere. In fact, I kind of wish I had done this different. I'm going to back this up just a tiny bit. I'm not going to change my answer. 1/2 V squared plus, this is 1/5. This comes out to be 1/2, let's see, plus 1/5. That's 5/10 plus 2/10. This comes out to be 7/10. 7/10 V squared. That's 1/2 plus 1/5 equals GH. So we end up getting that V is the square root of 10/7 GH. Again, remember free fall is 2, generally. Oh, we're solving for H. I did that so wrong. I know, I'm solving for H. So H is going to be 7/10 V squared over G. If we plug in the 6.50 and the 10 times 9.80, we get H equals 3.02. I just kind of wanted you to look and see how the 1/2 V squared and the 1/5 V squared would add together. All right, let's do the cylinder. The premise is the same. We don't have to erase any of that. That's still exactly true. We now have 1/2 M V squared. 1/2. We have a different I. That's what changes it. I this time is 1/2 mr squared. Omega is still V over R squared equals mgh. Once again, the m's all cancel. This r squared here cancels with this r squared here. And I get 1/2 V squared plus 1/4 V squared equals GH. So 3/4 V squared equals GH. This is basically, if we multiplied by M, that would be our kinetic energy. So H equals 3/4 d squared over g. Put in my numbers. And like I say, you can put numbers in earlier if you like. And when I saw that, I was wrong. Was I wrong? I was wrong. And I'll tell you why I was wrong. I was thinking about the problem wrong. All right, it went higher. Why did it go higher? I said it took more energy to rotate. Won't it not be able to go as high? That's where I messed up. The kinetic energy before it starts rolling, the sphere does not have as much kinetic energy. Because the sphere has a smaller moment of inertia, at the same speed, it has a less total energy. If it has less kinetic energy, it will not roll as high. The sphere is going to stop. The cylinder will keep going. The cylinder has to have more energy to go 6.50 meters per second. So the cylinder had more energy before it rolled up the hill. I had the right idea in my brain, but I said it exactly wrong. Talk that through one more time to clarify. If you have a solid cylinder and a solid sphere, and they're rolling at the same speed, in this case 6.5, in order to roll at the same speed, a cylinder requires more energy. It has more kinetic energy. Greater moment of inertia, greater rotational kinetic energy. Because it has more kinetic energy at the beginning of the problem, when it has converted all of it to potential energy, it can actually roll to a greater height. Okay, so only one more thing I want to point out. I'm not even sure if you need it, but you might. Might be on some of the homework. And that is, what is the direction of angular quantities? Okay, usually when we talk about direction for angular quantities, we talk about something that's either rotating clockwise or rotating counterclockwise. It's one of the easiest and probably the most frequently used idea at this level of physics. However, we do treat it, angular velocity and angular acceleration, as vector quantities. Technically, there's something called a pseudo-vector. If they're vector quantities, what's the direction of the vector for something like angular velocity? It's real obvious what the direction of the vector is for linear velocity. It's the direction that the object's moving. Okay? So, basically, if you have something rotating, and it is rotating counterclockwise, then the pseudo-vector, or the angular velocity when you treat it as a vector, is out of the page, or out of the board in this case. It would point as a vector straight out to you. Sometimes you'll see that drawn with a dot. Sometimes they'll put a circle with a dot. You're supposed to think of that dot as being the tip of the arrow coming out at you. If you have an angular quantity and it rotates clockwise, then that is going to have an angular vector that points into the board. We use a little X for into the board. You're supposed to think of that as the tail feathers of this arrow, whereas you would think of this as the tip of the arrow. If we want to draw something in 3D, here's X, here's Y, here's Z. So to kind of picture that third vector. If I have something that lies in the XZ plane, and it's rotating that direction, coming out this direction, so picture it in the XZ plane, that would have a velocity vector. Use something called a right-hand rule. If you put your right hand with omega, your thumb will point in the direction of that vector. So if it's going this way, my thumb points out of the board. If it's in this XZ plane, my thumb points straight up. So in this case, omega points along the positive y-axis. I think it's possible there might be some angular quantities on maybe the Mastering Physics multiple choice. It's good to understand how to do that. Just take your right hand, fingers go with the angular velocity. Your thumb will point in the direction of the vector. All right, I think that's enough for Chapter 9. That gives us plenty to talk about when we have class.